Do we have any announcements today? We're just chugging along. It will be office hours this afternoon. All right. Very good. So we're talking about this extremely important problem, the most important thing we'll study this semester, the problem of Rabi oscillations. So importantly, what we learned is that the problem of looking at the spin magnetic resonance for a spin 1/2 particle is really the problem of control of quantum coherence of the position. So if we want to, and this is sort of the basis for thinking about any kind of control of quantum superpositions. So understanding spin magnetic resonance is just the whole story. And it's really one of the most important things we'll study this semester. So as we have said now many times, we're going to look at this problem of thinking about spin magnetic resonance, where we have this bias field, and we started with this rotating transverse magnetic field. And in the rotating frame, we have this Hamiltonian, which is in the rotating frame is a static Hamiltonian, and thus one that we can look at the dynamics then easily. So the time evolution operator is easy to write down in that case, and it's the rotation matrix in a 2D Hilbert space, an SU2 rotation about a certain axis with a certain precession angle. And that precession angle depends on this generalized Rabi frequency, and the axis of the rotation is determined by the detuning of the Rabi frequency in this way. Okay? And so from that we easily solve for the probability, say, to be spin up if we initialize the system to be spin down, and we have this general solution. Okay. And that general solution, just sketched over here, are the Rabi oscillations, or Rabi flopping, as it's sometimes called. And what we see is that the probability to be in the excited state oscillates from 0 to 1 at a frequency of the Rabi frequency when I'm right on resonance, and oscillates at a faster frequency if I'm off resonance. Okay? And we can understand that and actually very easily do calculations as well by thinking about this evolution as the precession of the Bloch vector on the Bloch sphere, right? So we start, for example, with the system where the Bloch vector is on the south pole, and if I'm on resonance, then, well, actually, this is the left-hand rule, but never mind, it goes the other way. Precessing around that axis, and the then projection of the Bloch vector onto the z-axis tells me what the probability is to be in excited state or to be in spin up. Let's just quickly remind ourselves about that. Okay, so let's say I'm right on resonance here. Delta is 0. The precession frequency is the Rabi frequency, and at some time I am at some angle here. That precession angle then is omega t. Okay, that's that angle. So now I ask you, how do I turn that geometry into the probability to be in the excited state? So I can find the component, say, along the 3-axis or the z-axis of the Bloch sphere, right? So the component on that sphere is equal to what? So remember, we have a Bloch vector, Q, which is the expectation value of the vector of Pauli matrices, right? And as I said, it's kind of traditional in original, Bloch wrote these components as U, V, and W, and we'll do that as well. That's the X, Y, and Z component of this vector, okay? So the Z component is double Q. The X component is D, the Y component. Okay, so what is the W component at time t? Well, at time equals 0, it's -1, right? It's minus the cosine of that angle. Right? So, now I ask you the following question. What is the probability to be in the excited state? Or to be spin up? And how is it related to the components of the Bloch vector?
We have to write instead of theta over here too.
That's okay. So let's just say let's look at it this way. I give you the following question. I have a Bloch vector Q, general Bloch vector. Okay. What is the probability to be in any state given Q? How would you do that? I mean, there's all kinds of translations you can use. But the easiest way to think about this is to relate the density matrix to the Bloch vector. So how is the density matrix related to the Bloch vector?
Some vector has identity
Yeah.
plus u times the sigma vector.
That's right. Excellent. Excellent. Over 2. Okay? So now, I ask you the following question. What is the probability to be in the excited state, and how is that related to the component of the Bloch vector? So now I want to know, what's the probability to be spin up? How is that related? How do I get that from the density matrix?
Roach
Yeah, excellent. I got the sandwich. Diagonal element. Right? Which is equal to what? That's 1. And then it's the expectation value of that. Right? Which is only going to be what? So maybe I should, let me erase this. Let's write out some more steps. Right? And what's that? Well, if it's sigma x, what is it? 0. If it's sigma y, what is it? 0. If it's sigma z, what is it? 1. So it only has a z component. So this is equal to 1 plus w over 2. Okay? because that's the z component of q. Is everyone clear? And that I just erased, because I'm a bad professor, and that's equal to 1 minus cosine omega t over 2, as we said. We're going to come back to this through the course of lecture. It's really important that we be able to translate what we have is many different ways of mathematically representing the state of our two-level system. We have the probability amplitudes. What is the probability amplitude? We write it as a superposition of spin up and spin down if it's a pure state. We have the density matrix as a 2x2 matrix. We have this vector in three-dimensional space. They're all different ways of writing down the quantum state. And we need to learn and get more comfortable with how we translate between these different ways of expressing it more easily. Because we go back and forth all the time. Yes, I'm listening.
It is a case for on resonance,
Yes.
but
So off resonance. Yeah, you think about that geometry. So now you have to think about what this angle is and what that probability is as a function of time. You have to do a little bit of geometry. I'm not going to do it for you. But it's not that hard. All right. Also importantly, last time we talked about the rotating wave approximation. So the rotating wave approximation is when we say, well, let's say instead of having a rotating magnetic field, we had a linearly oscillating magnetic field somewhere transverse to the axis, right? When we have that problem, then in the lap frame, we had this problem, right? Yes, sir.
For this case of the linearly oscillating external field, does the definition of the Rabi frequency omega change from gamma beta 0 to gamma beta 0 over 2?
You mean beta perp? Yes. So gamma beta 0 is the resonance frequency.
Oh yeah, yeah.
The Rabi, and you're correct. So let me flesh that out a little bit. Okay. So I'm writing here. I've still defined the Rabi frequency. So there is a subtlety here. It is a little bit confusing. We'll come back to this because it's going to kind of bite us a little bit later in the lecture. But I've still kept this to be resonance frequency, and I've still kept this to be related to the strength of the field. Okay? I haven't done any factors of 2 yet. Now, as you're suggesting, so this is equal to 1/2 e to the minus I omega t plus phi plus e to the minus I omega t plus phi. That's cosine. And then sigma x is sigma plus sigma minus. Okay? Now there's this crazy factor of 2 out here, which, as you're correct, is now gamma over 4. I mean omega over 4 rather than omega over 2. All right? So, if we go to the rotating frame, and I'll come back to this factor of 4 and factor of 2 in a moment, then we have Longmore's theorem. We subtract off the fictitious magnetic field. Oh, one of these guys got me plus, huh? So far we've gone to the rotating frame. We have made no approximations. I just went to the rotating frame, and going to the rotating frame, subtracted off the fictitious magnetic field, and made these guys time dependent. The rotating wave approximation which is valid when the detuning and the Rabi frequency are tiny compared to the resonance frequency. So this is a near resonance approximation and a perturbative approximation. When that is true, then we can neglect the counter-rotating terms. So there are the co-rotating terms where the time dependence cancels. And then there are the counter-rotating terms, which oscillate extremely rapidly compared to the dynamical evolution frequencies that are determined by these amplitudes. So when this is true, we can neglect the counter-rotating terms. That is what is known as the rotating wave approximation. And then the rotating frame Hamiltonian is approximately equal to that. So this looks just like what we had in the rotating case, but with half the amplitude, because only half of the amplitude is co-rotating, and the other half of the amplitude is not. So there's a vector factor of 2 there. Now that factor of 2 is very, 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 very specific to true magnetic resonance. We're going to talk in a moment about pseudospins and qubits and two-level atoms where that factor of 2 doesn't appear. So we have to be, it's going to be confusing. We will see. All right. Very good. Now, I just want to, we talked about different representations. Again, I want to emphasize them here. Let me use this picture of what we talked about in terms of thinking about the dynamical evolution. We have different representations. If we restrict ourselves to a moment to pure state, which is what we're talking about, although we'll hope to generalize that before lecture's end. We have a ket, right? We have a spinor, which is a column vector in a basis, right? We have the density matrix, or density operator. Which is that. We have the density matrix. Which is the matrix representation of this. And this outer product is the matrix right? And then, of course, we have the Bloch vector. Q. So now I ask you the following question. How many parameters does it take to specify a pure state in this two-dimensional Hilbert space? How many real parameters? And how do I reconcile that with all these different representations? So for a pure state, not an arbitrary mixed state, of a two-dimensional Hilbert space, a qubit, how many real parameters does it take to specify the state? Two, right? Now, how many, but the Bloch vector has three parameters, u, v, and w. So how come I have three parameters here, but it only takes two? Yeah. Because the length is fixed. So if it's a pure state, we have a constraint, which is that u squared plus v squared plus w squared is 1. It's a unit vector. Bless you.
Thank you.
All right. What about here? This is a matrix with 4 entries that, how do I reconcile the fact that there are only 2 parameters needed to specify the state? Yeah?
Because they're really specified by the bra and cat.
They are. And that is manifest in the relationships that we have here. For example, if this is normalized, assumingly, so that means that this plus this is always 1. So we always have, for a normalized density matrix, if it's a d-dimensional Hilbert space, there are always have to subtract off these guys. So there's only one independent parameter here. There would generally be 2 other parameters here. This is the conjugate of this, so I only need, this is the complex number, so that looks like 3 parameters. But the fact that it's a pure state is another constraint, which says that the trace of rho squared is also 1, right? So that's another constraint, and that makes these what looked like 4 independent parameters down to 2, and similarly. Okay. Once again, we can look at this, and now I ask the following question: how are u, v, and w, that is to say, the x, y, and z components of the Bloch vector, related to the probability amplitudes in the spinner? Okay, so u is equal to this, right? Which is equal to plus the complex conjugate, right? And this is the thing that takes me from spin down to spin up. right? So this is the probability amplitude to be up. When I don't write the sub z, that's a standard basis, so that's what I'm always writing. And this is the complex no, it's down, what the heck am I saying? And this is up, star. Okay. So, this is equal to twice the real part of C down, C up, star. It's that plus its complex conjugate is twice the real part. So the off-diagonal element of the density matrix, as you remember, is something about the coherences. And the V component of this is equal to minus I that plus complex conjugate, using the fact that sigma y is sigma plus minus sigma minus over I. And so this is equal to twice the imaginary part, and this is rho down up. Twice the real part, I mean the imaginary part, of C down, C up star, which is twice the imaginary part of rho down C up. So, the U and V components of the Bloch vector, as we expect, say something about the coherence in the superposition of up and down along Z, right? Because they represented the components on the equator of the Bloch sphere. And what about W? Well, that is C up squared minus C down squared, right? Or equivalently, it's the population inversion. That is to say, it represents the difference between the population in the excited state and the population in the ground state. So, with this, we also know that this is normalized. The total probability to be either in up or down has to equal 1, right? So if I sum the population in the excited state plus the population in the ground state, that total probability is 1. So that's another way of getting the formula that I wrote a moment ago without going through the rigmarole of writing the dot product of blah, blah, blah. You just can look at this and now see that the population in the excited state is 1 plus W over 2, and the population in the ground state is 1 minus W over 2, right? Just with these two equations. Either add or subtract them, and you get this. These are relations you have to have in your head. All right. So when looking at the dynamics of this Rabi oscillation, we can look at it in terms of the dynamics of the spinor, or we can look at it in terms of the dynamics of the Bloch vector, as we did just geometrically by looking at the precession of the vector on the sphere. But I can also write in differential equations, and these are known as the Bloch equations, because Bloch wrote them down, thinking about dynamics of the spin. So the Bloch equations are another way of expressing the dynamics of the spin, but in terms of the Bloch vector. And we had written that down because from a Heisenberg perspective, we had this equation. This was the equation of the gyroscope, right, that we wrote down. So if I take the expectation value of this, it says the Bloch vector obeys a gyroscope equation. Just taking the expectation value. This is the equation of precession of a vector on the sphere. Okay. And we can write the components of that. If I look at the ith component of that vector, that is epsilon ijk omega tote sub j q sub j. So this is some generator of a rotation matrix in 3 dimensions. It should be sub k, yeah. This is a generator of a rotation matrix. And if I write out the components, I get the following. It's an anisymmetric matrix. Its diagonal elements are 0. So the equations of motion can be understood as equations. This is for the phase being 0. Yes, sir.
At the last lecture in the 2D Hilbert space,
Yeah,
you had a 2x2 matrix.
that's right.
Also had delta and omega.
That's right.
So this has the same number of parameters.
It does. And that's exactly the point. We had 2 different representations of the same physics. One was thinking about a spinner in Hilbert space. And that spinner in Hilbert space has complex coefficients, and the generator of the dynamics was the Hamiltonian. And that Hamiltonian was the generator of an SU2. So as you said, we had another equation, which is this equation. This is the Schrödinger equation, written in the basis of, this is the Hamiltonian, in the rotating frame, with the phase 0. This is a different way of expressing exactly the same thing. And that's what I was getting at over here. This is an expression for the evolution of the Bloch vector, which is a parameterization of the density matrix. But there are 2 different ways of encoding the same information. This is the dynamics of a vector in Hilbert space. This is the dynamics of the Bloch vector, which is another way of encoding the same information. And they go back and forth between one another here, the relationships of them. So for example, if I took the time derivative of this density matrix, I could take that time derivative, put the Hamiltonian in, use the commutator, and then take expectation values, I get this equation again. So, said now fully, I have 3 coupled ODEs These 3 equations are also known as the Bloch equations. For example, let's solve these equations simply when delta is 0. So let's say we were right on resonance. Okay. Then in that case, the u component is constant. The phase, I also set the phase of the oscillator to be 0. The v component minus omega w, and the w component is plus omega v, right? So I have, in that case, just these 2 coupled ODEs. So now I ask you, how do you solve this? Take another derivative, right? So let's just do that. Yuck. Right? So, with that said, we have omega squared. Right? So what are the solutions to those equations? So it goes to the signs. That's a simple harmonic oscillator equation, right? So we have, for example, the population inversion satisfies that equation, right? Those are the initial conditions. And what if I start in spin down along the z-axis, what is W at time t equals 0? Is that the south pole? Minus 1. Minus 1. Because it's the difference between up, population up, minus down. If it's all down, it's minus 1. Which is exactly what we had just using geometry at the beginning of this. So we have so many different ways of looking at the same thing, and we just need to be able to go back and forth between them. All right, very good. All right, so now I want to turn our attention to to the next important star of our show, which is the two-level atom, which is what really motivated this discussion in the first place. And we want to talk about Rabi oscillations in terms of coherent driving of a two-level atom by a coherent laser. Okay? So in the two-level atom, what we said is we have two energy levels. Typically, one of them is thought to be the ground state. And there's some excited state, which we typically call E. Of course, there are a multitude of such states, but we're going to pick one particular one with all the quantum numbers specified. And then we're going to, there's some energy difference between them which determines the resonance frequency, according to the Bohr formula. Okay? And now we're going to shine a laser beam on this atom with some monochromatic laser. We're going to ignore anything about its line width or anything for the moment. It's got some good, well-defined frequency, the frequency of the laser. And that's going to be tuned very close to resonance with this. So we typically draw it like this with some laser frequency. And there's a detuning, which is the difference between the applied frequency and the resonance frequency, just like we defined the detuning in the spin magnetic resonance case in terms of the frequency of the applied perturbation compared to the resonance frequency. Okay? Now, we're going to assume that this is a dipole allowed transition, electric dipole allowed. As we discussed a few lectures ago, if we make the electric dipole approximation, which is a good approximation when we're talking about optics, because the laser wavelength is in order of 0.5 micron and the atom is on the dipole size is on the order of angstroms in this kind of general typical problem, then my interaction Hamiltonian in the electric dipole approximation is this, where this is the electric field of the laser at the position of the atom. And we're writing that classical field here as being monochromatic and polarized. Okay? So this is the polarization. This is the frequency of the laser. And then there's whatever the phase is at the position of that. So for example, if this were a plane wave, this would be K dot R, right? That would be the phase at that position. Notice I've chosen a different sign convention to the one we had before because this is typically how you would do it. It's because you have either the plus I, K, R. Okay? Yeah.
So we're not thinking about like the atom spin and the magnetic component of the light?
It's all there. I mean, the atom has a spin. Typically, it has an electron spin. It typically has nuclear spin also. But to lowest and good approximation, the interaction of the atom with the light is completely dominated by the electric dipole moment. Okay? Unless this is a dipole forbidden transition. These E and G's, as you say, have generally quantum numbers that specify things like the hyperfine structure or whatever, all the quantum numbers that specify the good energy level of the atom. But I'm not specifying what they are. I'm just saying there is two states, they're labeled by whatever quantum numbers label this one and whatever quantum numbers label that one, and these guys are connected. Now, there is an important point here, which has to do with selection rules. Because depending on the polarization of the light, affects what excited states are connected to what ground states. So, for example, you may or may not remember that there are these selection rules. For example, let's just ignore spin for the moment. And let's say my ground state is an L equals 0 state, a so-called S state. It has one sublevel, right? My excited state then has to be an L equals 1. A P state. It has M sub L equals -1, 0, and +1. Right? These are the Zeeman sublevels. Okay? So now I ask you, what are the selection rules? In other words, can I, with a laser beam, excite here? Can I excite here? Or can I excite here? Are all of those allowed?
Depends on the helicity.
That's right. They're all allowed, but it depends on the polarization of the light relative to what I'm calling the z-axis. Okay? So, unfortunately, we have letters that take on many different meanings here. We typically call this a pi transition, a sigma plus and a sigma minus. Now, having nothing to do with the Pauli matrices, it's just because in German, S is perpendicular, and they like the Greek letters, and P is parallel. I don't know, I don't speak German, or I do, but that's the best I can do. Anyway, so the point here is that if this pi polarization is the polarization along Z, this is right hand relative to Z. And this is left hand relative to Z. Not relative to the K vector. It's whatever I call the quantization axis of the atom, which might be along K, but it doesn't have to be. So, for simplicity, I'm going to just for the moment think about this is linear polarization along the quantization axis, and call this guy G and this guy T. I can generalize this, put in hyperfine structure and all of the doohickeys, as long as it's an allowed transition with the allowed polarization. But for the moment, I will consider this kind of transition just for simplicity. All right? So, in that case, epsilon is real. Okay? If it's linear polarization. All right, so let us remind ourselves then, in the two-level atom approximation, what that means is firstly, I only need to consider these two levels in the whole uncountably infinite Hilbert space of bound and unbound states, I can just now say it's a two-dimensional Hilbert space. These are the only two levels in which there will ever be any substantial population. I can just ignore all the rest. Okay? In that case, then the dipole operator is equal to, well, it only, as we said, these guys have are parity eigenstates, and so there are no diagonal elements, as we discussed some lectures ago, only off-diagonal elements. So there is a when restricted to that, to the Hilbert space, that's all I got. Okay. Now, I can always choose the phase of the wave function such that this is a real number. So this matrix element I'll call VEG. And by choosing the phase of the wave function appropriately, I can make this real. Okay. I don't have to do that, but it simplifies my life. And so what I get is a vector. Okay. All right, let's put it all together now. So now I want to write down the Hamiltonian of the system. The Hamiltonian of the system involves the Hamiltonian of the atom and the interaction Hamiltonian, which I think in the notes I called the atom laser interaction. So, the total Hamiltonian, which is time dependent, is the Hamiltonian of the atom plus the atom laser interaction. The atomic Hamiltonian, restricted to the two-level system, I have its diagonal in the basis of its eigenstates. And in this case, I'm only keeping those two eigenstates, E and G. And so, my Hamiltonian now takes the following form. Okay, so one very important thing we have learned, is that any two-level system is isomorphic to spin 1/2. So as long as I map two orthogonal states to the standard basis, I can map this onto a spin, or what really is a pseudospin, also known as a qubit. So my two-level atom is a pseudospin. And the standard mapping is to say the ground state is spin down along Z, and the excited state is spin up along Z. Now, I emphasize something here. This has absolutely nothing to do with the spin of the atom. Nothing. Nilch, zero, nada, niet, no. Cat, hat, I don't know, chapeau. It doesn't matter, it's nothing. This is just a mapping, okay? It's just a mathematical mapping. So, with that said, what I see is the following. In this pseudospin, this is equal to where I have defined this energy, dipole, but there's a minus sign. So I have defined this energy with the minus sign as h bar omega. So the Rabi frequency here, it's times h bar as an energy, is the interaction energy. It's the interaction energy that depends on the dipole matrix element, the electric dipole matrix element, and the amplitude in the electric field. Okay. This is the Rabi frequency. Okay. Sigma plus takes me from ground to excited, as I say, spin down to spin up. This is sigma minus, right? Okay, so I say that every two-level system, a Hamiltonian for any two-level system, is equivalent to the Hamiltonian of a spin or a pseudospin in a pseudo magnetic field. Not the magnetic field of the magnetic wave. It's a pseudo magnetic field. PS pseudo. All right. So, how do I express this in terms of an effective Rabi frequency? Well, the thing I should always do is express this in terms of the Pauli matrices. I've already done that, sort of. What about this term? So as we said, this is always equal to some amount of the identity plus some amount of the Paulis.
Get rid of the identity.
Get rid of the identity. And how do I do that? Well, I have to look, the A is the trace, right? This is equal to 1/2 the trace of the Hamiltonian times the identity matrix, right? When I take the trace of that. So, what is this component? Well, that's the trace of the matrix, which is the sum of this and this. Excited plus ground, right? So this is equal to E, the sum of these energies over 2 times the identity, plus the difference of them over 2 times sigma z. Because this term is the trace with sigma z, which is the difference. Think about it. Okay. This is h bar times the resonance frequency over 2. The resonance frequency, as we said, was h bar omega is equal to the Bohr frequency. You with me? So, we can generally, from the point of view of the dynamics, ignore this. That doesn't affect anything about the dynamics of the system. And now write the Hamiltonian as the following. I should I'll leave that. Let's come back. Let's look at this. The Hamiltonian of my two-level atom is equal to h bar omega over 2 sigma z plus h bar Rabi frequency over 2 sigma x cosine omega laser t plus phi, or minus, where the resonance frequency is given by the Bohr formula, and the Rabi frequency is the component along this minus sign. The dipole matrix element is negative because the electron charge is negative, so it's a positive. What can you tell me about that Hamiltonian? Okay. No, there is no 2 in the denominator. Absolutely not. Thank you, Sheila. Yeah, absolutely not. Okay. Okay. So, what can you tell me about that Hamiltonian? Yeah, so this looks like the problem that we had before of a spin with a resonance frequency. So this plays the role of the bias B naught, right? So that was like our omega naught. The resonance frequency, which was the splitting here, that was the splitting for spin up and spin down, was due to the static field, right? And this plays the role of the transverse perturbing field. Which creates coherence between these two by causing Law-Moore precession on the Bloch sphere between spin down and spin up. This looks like the problem that we solved with the linearly oscillating magnetic field, right? So we have to go to the rotating frame, but then we need to make the rotating wave approximation. Notice that, as Shiva pointed out, there was no factor of 2 here, so now it comes back, and we don't have that factor of 4 that we had for the real spin. But the pseudospin doesn't have that. So, in the rotating frame, in the rotating wave approximation, we have approximately, neglecting the counter-rotating terms, Notice there's a difference in the sign here that we had before because of the way that the phase was defined with an omega minus rather than omega plus.
Is that first term your sigma plus?
No, it's sigma z. Yes. So, we have exactly the problem that we solved before. And so, what happens in this case is the following. If I start the atom in the ground state, right? Which it will be if I have an atom where the high energy transition is an optical frequency at room temperature. This gap is huge compared to this is, you know, hundreds of terahertz compared to room temperature, so I don't have to worry about excited state. And now I turn on this laser and I tune it close to resonance. What's going to happen? Well, what's going to happen is I'm going to start getting probability amplitude in the excited state. And in such a way that the atom gets to be in a coherent superposition of the ground and the excited state. What I will see, just as before, is now, if I start the atom in the ground state, here's my Bloch sphere. And if I set the phase at the position of the laser to be 0, then the atom, I process around this axis of the Bloch sphere, and I will rotate around that. Of course, this is going around in the rotating frame at 10 to the 15 cycles per second, but I'm ignoring that. I'm going onto the rotating frame. And it's at a time equal to pi over the Rabi frequency, I'll end up here, which is to say G minus IE over root 2. And then at a time equal to pi, I'll be in the excited state. And then at a later time, 3 pi over 2, I'll be in this state. And then at a time 2 pi, I'll be down there. And the system will Rabi oscillate between those two. So if I did a pi over 2 pulse, which is to say, this time I create that superposition state. And by modifying the phase of the laser, at a later time I can manipulate the phase of the superposition. So if I phase shift the laser for a second pulse, that can change the axis of rotation depending on the phase of the laser, and rotate around a different axis and create a different phase. Yeah.
So we're not worried about our lifetime of our...
Oh, we're not yet. Yeah, we didn't get there today, so we'll get there next week. That's the next thing we have to do. Indeed, we do have to worry about the fact that these states are not stable eigenstates. They spontaneously emit. That's critical. We're very worried about that, but not right now. All right, very good. So I want to just now connect, thinking about, as we will do, one of the things we're getting is how does this compare to the Lorentz oscillator that we discussed at the very beginning of the semester, thinking about a charge on a spring that had a natural resonance frequency. We're going to get there. But the first thing I want to think about is how we relate certain aspects of the induced dipole moment to the representation of the quantum state. So let's look at how does the dipole moment, the expected value of the dipole moment, evolve as a function of time. Okay? So, what is this equal to? Well, first thing we need to do, we're in the rotating frame, so all of the all of the operators and states need to be in the same picture. So we have to go to the rotating frame to write the dipole in the rotating frame. So this is equal to the state in the rotating frame at time t, the dipole operator in the rotating frame, so let's go to the rotating frame. Our dipole operator in the Schrodinger picture, we said was dEg sigma plus sigma minus. We had only those. So this is in the Schrodinger picture. To go to the rotating frame, I have to do the unitary transformation. And when we did that, that's rotating around the pseudo z-axis. And again, this direction of the Bloch sphere has nothing to do with physical z in space. It's just, really we should call it the three-axis, the one-axis and the two-axis, although we always call it, related z. But we have to remember that this has nothing to do with the z direction of the polarization. So, we're rotating around the pseudo z-axis, and when we did that, we get e to the plus I omega lt plus. Remember, we're going to this is the frame that rotates around the z-axis by a precession angle depending on the applied frequency, the laser frequency, right? When we went to the co-rotating frame, we co-rotated at the frequency of the applied field. In this case, the frequency is the laser frequency, optical frequency. All right? So, with that said, my expected value of the dipole operator as a function of time is equal to the blah, 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 dEg. Oh, there's no hat on this. That's just a number. I have the expected value of this guy as a function of time. Write that down. Plus right? And this is the thing that takes me from spin up to spin down. I forget about this. Just understand that's what we're talking about. This thing that takes me from spin down to spin up. So this is equal to, for this case, for the pure state, this is the probability amplitude to be down, and this is the star of the probability amplitude to be up. And then I have the other way around. Let me write it this way. Which is equal to dEg times twice the real part of this guy. I like to write e to the minus I. So, what we have is that the dipole moment of this atom its expected value is the following. Twice dEg, the real part of rho up down e to the minus I. Which is equal to twice dEg, the real part of this cosine omega LT plus twice dEg times the imaginary part of rho sine. So, I want to emphasize a few points before we conclude. What we see, as expected, the amount of dipole I've made depends on the coherence between up and down. Because neither the ground state nor the excited state alone have a dipole moment. It's only the superposition, the atom's superposition of ground and excited that has a dipole moment. It's only then that there is an asymmetry in the probability density of the electron cloud away from the nucleus, so that there's a dipole moment on average. Otherwise, the electron cloud is symmetrically, probability-wise, there's equal amount for being in this direction versus that direction. It's only when I have a superposition of them that I have that. And the amount, there's always going to be, as we always have said, when we have this driven system, there is going to be a component that's in phase and a component that is in quadrature. Okay? This can be related to the components of the Bloch vector. Because we said that the components of the Bloch vector were related to the components of the density matrix. We're going back and forth between all these different representations all the time. So we remember that U was equal to twice the real part of this, and V was equal to twice the imaginary part of this, from what we had earlier, and W was related to the population conversion. This is the complex conjugate of this in the other direction. And so, with that said, we have that the dipole is equal to U sine omega t minus V cosine. I'll just conclude there just to say that what we see here is that the U and V components of the Bloch vector tell us something about the components that are in phase and in quadrature with the driving field. Oh, I got it backwards, don't I? Excuse me. Cosine, sine, pardon me. And as you remember from our earlier studies, the components that are in phase and in quadrature have something to do with the dispersive response and the absorption. Come back to that in a little bit. And see how this is or is not like a Lorentz oscillator. So that's coming up. All right.